Sometimes we can't take the derivative just by our usual techniques. Sometimes we have something called an implicit function. And an implicit function looks like this. Our x's and y's are mixed together, and it's really hard to solve for just y, so that we can take our derivative the normal way like we would in these explicit functions. Implicit differentiation uses the chain rule so that we can do that by taking the derivative with respect to x and then solve for dy dx. So how does that work? Well, let's look at this first example here. If we want to take the derivative of this, we're taking the derivative with respect to x, knowing that y is a function of x. So we take the derivative of this part. So the derivative of x squared with respect to x is 2x. And then the derivative of y squared with respect to x, we have to use our chain rule because y is a function of x. So we take the derivative of the outside part times the derivative of the inside part, because we're taking our derivative with respect to x, and y is a function of x. So then we take the derivative of 8, it's a constant, so the derivative is 0. Now, all we have to do here is solve for dy dx, and we'll have our derivative. So we have 2y times dy dx equals negative 2x. Divide by 2y, and so we have dy dx equals negative x over y. And yes, you still have y in there as part of your derivative, and that's okay. That's what happens most of the time with implicit differentiation. So decide which variable you're taking the derivative with respect to. Remember that the other variable is a function of that one you're taking the derivative with respect to. So in this case, we're taking with respect to x. Y is a function of x, so I have to use the chain rule to get its derivative. Now, if you wanted to take the second derivative, you could do that. We'd do the same thing. Bottom times the derivative of the top minus top times the derivative of the bottom, all over the bottom squared. Let's erase some of this so we have some room here. Hopefully you got that all written down. Now, we know what dy dx is. We already solved for dy dx. So we can replace dy dx with what we know it to be equal to. And then we just have to simplify. So we have negative, and then if we get a common denominator, our common denominator is y, so we have y squared plus minus x squared, and then we can bring that common denominator, multiply it down there, y cubed. So when you have your implicit differentiation and you have to take multiple derivatives, you're going to have to use the ones you solved previously excuse me, to plug in so that you can get those second derivatives. What if I ask you to find the slope of the line tangent to the curve, the sine of xy equals x at the point 1/2, pi over 3. Well, remember, slope of the tangent line, that means we're going to find the derivative. So we need to find the derivative of this. Well, it's not y equals something. We want to find the derivative with respect to x, but we don't have it solved. So what we need to do is use implicit differentiation. So we use our chain rule. So the outside part, the derivative of sine is cosine. And then the derivative of the inside part, we have first times the derivative of the second plus second times the derivative of the first. And then we take the derivative of the other side. Now, we can distribute this So we have x times dy dx cosine of xy plus y times the cosine of xy equals 1. So when we subtract this over, we have 1 minus y cosine xy, and then we'll divide by the stuff that's with that, and we have our dy dx. Make sure you check that and understand what's going on with that. Okay, now you can simplify this further if you want. It does simplify some more, but we're going to just leave it there for right this second. Well, let's go ahead and simplify it. Well, if you separate this, you've got 1 over x times the secant of xy, and then this, the cosines cancel, and if we factor out that 1 over x, so you end up with that simplified. Make sure you know how to simplify these. I'm assuming that you guys can handle all these algebraic simplifications. If you're having trouble with them, make sure you come in and ask for clarification. Now we want it at this particular point. So our x is 1/2 and our y is pi over 3. So our dy dx evaluated at the point 1/2 comma pi over 3 equals 1 over 1/2 is 2 times the secant of 1/2 times pi over 3, which is pi over 6, minus pi over 3. So now we have to use our unit circle. The cosine of pi over 6 is square root of 3 over 2, so the secant is the reciprocal of that. So it's 2 over the square root of 3. And multiply that through. You can't really simplify this more than just getting a decimal approximation, but that's fine. So this is the slope of the line tangent to the curve sine of xy equals x at 1/2 comma pi over 3. Now, getting these into your calculator to look at the graphs is going to be very difficult, sometimes impossible. So you need to make sure you understand how to do this algebraically. All right, let's look at one more. What if we want to find the tangent and normal lines to 6x squared plus 3xy plus 2y squared plus 17y minus 6 equals 0 at -1 comma 0. Now if you look at this, you'll notice it's an ellipse. Hopefully you remember that from your conics from last year. And so we're looking at this particular point on the ellipse to find the tangent and the normal lines. Remember, a normal is perpendicular to the tangent, so that means that we use that reverse reciprocal or opposite reciprocal slope. So the first thing we need to do is take the derivative of this with respect to x. So our first part, use that power rule, 12x plus 3, and then here we're going to have to do our product rule. First times the derivative of the second plus second times the derivative of the first. Here we have to use our chain rule. And then here we're taking the derivative of y, so, and then the derivative of constant is just 0. So what we need to do is rearrange this so we have things that don't have dy dx over on this side. So that would be, if we distribute this here, we've got 3 over here and the 3 here, so we'll have -12x and -3y, because we'll move this and this over to the other side because they don't have a dy dx with them. And then the other part will factor out a dy dx. So that's this, this, and this have dy dx. So we have 3x plus 4y plus 17. So dy dx is negative 12x minus 3y all over 3x plus 4y plus 17. Now, we're plugging this in. We want to evaluate this at the point negative 1 comma 0. So we plug in negative 1 for x and 0 for y. We have 12 over negative 3 plus 17. So that gives us 12 over 14, which you can simplify to 6/7. So that's the slope of the tangent line. Okay, so this is the tangent. So that means that the normal line slope is, that's right, negative 7/6. So now we use our y equals mx plus b, and you end up with y equals 6/7 x plus 6/7 for the tangent, and y equals negative 7/6 x minus 7/6 for the normal line. So this is the tangent and the normal. I'm going to assume that you know how to take a slope and a point and plug it into y equals mx plus b, figure out what your b is, and get your equation. If you're having trouble with that, make sure you come and see me. So, implicit differentiation. So that we can take the derivative of implicit functions, which means x and y is all mixed together, you can't really solve for y. So we define those, or we take the derivative of those using our chain rule, taking the derivative with respect to x. Make sure you pay attention to what you're taking the derivative with respect to. And then solve for the one that you want. You want dy dx, so you solve for dy dx. If they give you a specific point, you plug that in. If you have to take a second derivative, then you're going to have to use what you learned from the first derivative to plug in as well, so that you can get your function. Make sure you've read section 3.7 and written down any questions you have so that we can go over them in class.